Well, in this last video of the course, we will consider divergence, curl of vector fields, and some optional information, not in the syllabus, about generalizations of Green's theorem. So we have divergence, curl, and generalizations of Green's theorem. Okay, to start with, let us recall our definition of gradient f. Namely, this was f sub x, f sub y, f sub z, where, of course, I assume f is a scalar-valued function of 3 variables. Now, here we can regard this del part, okay, irrespective of f. So, we can consider del as a vector by itself. As follows, we can write del as del by del x, del by del y, del by del z. Of course, this is not a usual vector, but a vector operator. Okay? This means the following. If you put an f, that is, if you multiply it by a scalar-valued function f, the product of the first component with f means it acts on it, it's the derivative. Okay. So, and of course, the product of del by an f, just means you multiply each component by f, but this multiplication is action of the derivative. Okay. And del f is obtained by multiplying del by del x with f. Here this means del by del x, the derivative, f sub x, etc. Well, what's the point in considering this as an operator acting on scalar-valued function? Well, in this form, it's called the gradient operator. It's a vector operator, but actually gradient operator. Okay. Now, the point is that if we consider del as a vector, then if we take here not a scalar-valued, but a vector-valued function, we can multiply them as well, in dot product or in cross product. So, we can now define for a function f, which is f of x, y, z, g of x, y, z, h of x, y, z, the following. Now, we considered this as a vector, so we can take the dot product with f. Well, that means del by del x, del by del y, del by del z, dot, okay, FGH. Well, hence, it simply means f sub x plus g sub y plus h sub z. Okay. But why do we define these things? Okay. Well, these operations are so important in physics and engineering and technology that anywhere you look at, you see such things. In electromagnetic theory, in fluid dynamics, in mechanics, in all kinds of, in heat equations, and hence chemical engineering, anywhere you can see these things. Well, this is called the divergence of it. Well, if we can take the dot product of two vectors, of course we can take their cross product. So let us consider del cross f. Okay. Well, what does this mean? This means the determinant of ijk. Okay. Now, del was del by del x, del by del y, del by del z, and f was fgh. Okay. So the I component will be h sub y, okay, minus g sub z. The j component, okay, would be f sub z minus, how does that go? H sub x. And the k component, g sub x minus f sub y. That's the standard determinant operation, namely the cross product. But the multiplication always means you take that derivative. Okay, this is called the curl of f. Okay. Well, these things operate on different components in a different way, okay? But they have some nice properties. Okay, the properties, I will say some because there are lots of them. Okay, here we assume, okay, the components FGH have continuous second order partials. Okay. Well, the most important thing here is perhaps the following. If you consider the divergence, okay, and if you apply the divergence to a curl, okay, so, by the way, these are all differential operators. They differentiate. So this means, in some way, you differentiate all components of f 2 times. Okay, now, continuity of the second partial says that the order is not important. They cancel each other. So actually, you get 0. It's easily verifiable. I will not do that. Or, if you look at the curl of, okay, f, but f is a gradient. Here always lowercase means scalar valued. For the others, I will use arrows. Well, this is also 0 all the time. Of course, it's a vector. Well, if the second order partials are continuous. Or, for example, if you look at del dot, well, you must have a function But if you multiply it with a scalar valued function, here phi x, y, z is from R3 into R, whereas f is fgh. And fgh are also scalar valued functions. Well, what do we have here? Well, a vector times a scalar is a vector, so I can take the divergence. Now this, of course, in both cases, in phi and f, we have x, y, and z's. Therefore, this is a product rule. Okay. And the product is the dot product. So we take the derivative of phi. Well, obviously it is the gradient of phi dot f plus phi times the derivative of f, but that's the divergence of f. Okay, this is a scalar, and this is a scalar, so you are adding scalars, and you expect in the dot product some scalar at the end. Well, a similar thing happens if you take the curl of a phi times f. Okay, this being a vector again, you can, of course, evaluate it. So you must have a cross here, derivative of the first one, cross f, but phi is a scalar valued function. But when you take the derivative, in some way, you must get a vector, and this is possible if you consider del phi. Well, del phi is a vector. You take the cross product of the two, plus phi times the curl. Okay, this is scalar. I mean, this is a product, okay, not composition. So you have such properties. You have lots of them, by the way, which I will not go into details, okay? All are easily and directly verifiable. All you have to do is, instead of f, put fgh, calculate. Okay. Then you get all these properties. Okay. But del dot gradient of a function, okay, now phi is a scalar valued function, of course. Gradient phi is a vector. You take the divergence of it. Of course, everywhere you have x's, y's, and z's. None is a constant here, okay, but it's scalar valued. This is not zero in general. Actually, what is this? Okay, this is the divergence of, okay, del phi was phi sub x, phi sub y, phi sub z. Well, this is derivative with respect to x here, y here, z here. So it is phi xx, phi yy, phi zz. Okay. This is usually shown in the form del square phi, called the Laplacian operator. Okay. Now this is a very important operator. Okay. The Laplacian emerged in many physical and technical considerations, namely in, okay, again, mechanics, hydraulics, and electrical systems. Everywhere you have it. You have to solve, in general, certain differential equation, that is, derivatives are involved and so on, but with many variables, so it's called a partial differential equation, to get solutions for example, a potential function in an electrical system. or in a mechanical system. All of these are very similar to each other, mathematically formulated. So these operators are quite important. Well, we will remark about them a little bit at the end, but roughly speaking, the divergence, that is del dot f, if it is 0, okay, it means that there is possibly some rotation there, okay? Not straightforward motion, some rotational aspect. The curve, on the other hand, measures rotation. So if it is 0, it means there is no rotation. For example, in Maxwell's equations, in electromagnetism, you have the magnetic field has a 0 divergence. It's one of the conditions. Okay, so the magnetic field does not go out from a point directly, but it always goes between two poles. Okay, from a positive pole and a negative pole, and it goes in curves in rotation. So all these three-dimensional formulations use divergence or curl. Now, back to generalizations of Green's theorem. Okay, let us recall again that the conclusion, okay, I will not worry about the conditions here. The conclusion of Green's theorem says, okay, we wrote this a million times, p dx plus q dy is double integral of q sub x minus p sub y dA, where, okay, C is the boundary of R. This is important. Now, how can we generalize this? Well, roughly two ways. You can generalize the left-hand side and see what you get, and the right-hand side. So, the first one, okay, generalizing the left-hand side. Well, this is a line integral in plane. So how do you generalize it? It becomes a curve, okay, in space. So say C is a curve in space. Well, if C is a curve in space, of course, we have a third term, R dz, okay, because we have x, y, and z's, but we know what that means. It's similarly defined as in two-dimensional case. So if C is a curve in space, left-hand side is okay. We already considered that. But what happens to the right side? Okay, but okay, recall that R should be, okay, bounded by C. Well, if you have a closed curve in space, okay, what does it bound? Well, in plane, it was obvious, the inside of C. But in space, this is a little bit tricky. So, for example, okay, if you have, say, a curve like this, and then it can bound, okay, a surface. So this is a surface. So, okay, if C is a space curve, then R needs to be a surface in space, a surface piece, actually. Bounded by C, a closed curve. It bounds somehow this surface. Now, well, we know double integrals, but we do not know what happens if R is a surface in space. This is a little bit problematic. Okay. This means that we need to define something like a double integral, but okay, S is a surface. So this is one problem. A second generalization is the following. Well, this time generalize, okay, the right-hand side. Well, the right-hand side is a double integral. If you generalize it, it becomes a triple integral. So, say, okay, right-hand side is a triple integral. Over some t. Well, but Green's theorem, the idea of the Green's theorem says that on the left side, C must be bounding t. So, but, okay, C was boundary of R, okay, in Green's theorem. So here, okay, well, C must be replaced by the boundary of T. But T is a solid in space. Okay. If you have a solid in space, its boundary is a closed surface. So, okay, we need to replace C with a closed surface, S. So again, we need a surface integral. Now, from our considerations, in both kinds of generalizations, we came across the necessity to define a surface integral. Well, it's a topic by itself, so we will not consider that in detail, but very shortly, let me say, okay, informal definition. Short, rather, explanation. Okay. Let S be a surface. Okay. Say Sij is a partitioning into smaller surfaces. Okay. And then consider limit of this sum, okay, of your f of Pij stars times the area of Sij's. Now, Sij's are surfaces, so this is surface area. You multiply by this, and then you add, okay. We show it by integral over the surface. Now, this is a surface. f of xy, rather z as well, okay, times the sigma. This represents, okay, surface area element. Now this is very similar to ds, the arc length element, but with one dimension added to it. I will not go into that. But important for us is the following. Okay, in vector form, okay, we have integral over S, the surface integral. Okay, we have a vector here, namely PQR. Okay. As in the line integral case, we take the dot product with n, and then we evaluate in the usual way as this limit, whatever that is. This is not our concern right now. But important thing, this n is perpendicular to S. Okay. Why do we take the perpendicular component of force? Well, because if you remember from your physics, we calculate flux in physics. Okay, flux is the vertical force to a planar part times the area of that part, and you add them. So you need verticality here, so we need a vertical unit normal. Okay, so this is the form, the second kind of surface integral using this one. Okay. Now, having not, let me not say defined, but roughly explained what we have there, okay, let me also say that this is called the total flux, okay, of F, which is PQR here, through S. So obviously, if S is perpendicular to the direction of PQR all the time, that is, okay, let us think a little bit physically, okay. If we have a surface, okay, and if this is the force, then you multiply the vertical component, okay, with the area, and then add. That's surface integral or flux. But if the directions, the normal of the, not plane, but the tangent plane, and the force are, say, perpendicular, then there is no flux. Flux is zero, because it just passes from both sides. Okay. So you need a perpendicularity there directly. Okay. So it's called the total flux. Now, having defined it, now let us relate it to divergence and curl, because these play a very important role. Okay. Now, forget that, and let us go back to, now, okay, let me say, reconsider, okay, u sub x minus p sub 1 in Green's theory. Okay. Observe the following. U sub x minus p sub 1, okay. Now, I can regard it, okay, as minus p in the second position and q in the first position. That's to say, I can consider qn minus p. Now, I take the derivative of q with respect to x, and I take the derivative of minus p with respect to y. Well, that is divergence. Because this was del by del x, del by del y. So take the derivative of this with respect to x, of this with respect to y. So this difference actually is a divergence. But at the same time, Q sub x minus P sub y can be regarded as del cross PQ. Well, in cross products, we know we need to add a third component, 0 if we have only 2. But this is precisely, okay, 0, 0, Q sub x minus P sub y, if you calculate that. And hence, this is the third component. In other words, the projection in the k direction. So, it is the curl of PQ, 0 of course, but it's the third component. Because we are in a plane, the cross product will be perpendicular to the plane. Now with these observations, let us go back and see what Green's theorem tells us, so that we can generalize them and finish our discussion. Now, again, this time back to Green's theorem. Okay, it says that we have P dx plus Q dy is R Q sub x minus P sub y dA. Okay, now, first of all, we generalize this to a three-dimensional thing, so this will be a surface integral, as we remarked. So, in left-hand side generalization, okay, right-hand side must be a surface integral over S bounded by C in space. Okay. So let us look at the right-hand side. Okay. Now, to be a surface integral, well, this is, of course, we get clearly the following. This is P dx plus Q dy, still in Green's theorem. This is the double integral over R of del cross PQ0 dot K, okay, dA. Okay. Now, this K is clearly perpendicular to R. So to generalize it to a surface integral, okay, we get, okay, remember R was replaced with a surface. We had del cross, but we don't have 0 anymore. We generalized to 3 dimensions. Dot, now this must be a unit vector perpendicular to S. Okay, and dA becomes dC. So we get the following. Okay, integral over C, PQR, okay, dot N ds is surface integral of del cross PQR dot N. Now this is perpendicular, but this one was parallel, dC. Okay, or just with F PQR, just integral C F dot N ds is del cross F dot N dC. It's called Stokes' theorem, a very important theorem in applications and of course in mathematics. Okay. So this is the one generalization we get over there. Now in right-hand side generalization, okay, we need a surface integral, okay, over closed surface S bounding T in R. Okay. So we need a perpendicular vector to S. We need an N which is perpendicular to S at each point. Okay. So in Green's theorem again, we have C P dx plus Q dy, which was R Q sub x minus P sub y dA. Okay. Now, we could write this as integral C PQ dot N ds, but N is parallel C. We need perpendicular. So we can manipulate a little bit. Namely, okay, write, okay, this N in a perpendicular way. This N, of course, is in the direction dx dy. Okay, write dx dy. Okay, well, before that, maybe I should say, yes, here. Okay, write the left-hand side, P dx plus Q dy, as okay, P minus Q. No. Okay, just this way. Minus P dx plus Q dy. Now, why I'm writing it in this form will be clear in a minute. Okay, that means, of course, that I have C, and then I have minus PQ, okay, dot minus dx dy. Okay, and then, of course, I have the other parts coming. Now, what's the point? Well, now this is perpendicular to C. Clearly, because C is parallel dx dy. So if you multiply, if you take the dot product, no, something is wrong. In the dot product, I have P dx, that's right. I have dy. No, I have to write Q minus P. Let me check in a minute. Yes. Q minus P is a better argument. And that makes me minus dx and dy here. Right, now it's correct. So I changed nothing actually. This is P dx plus Q dy. It's a dot product, okay? But now dy minus dx is perpendicular to this one. Take the dot product, you see it is 0. So it is in the form of a surface integral. I have a normal vector to C, but C will be a surface in a minute. So generalize. Okay, so generalization will become, okay, the closed surface integral instead of C, okay, and this would be, no, before this, let me write it again in this form. Yes. This is now Q minus P dot N ds. But this is, ds is the same because changing the places of the x dy does not change their magnitude. So this is now perpendicular to C. So we put it in that formulation. Well, now forget this. The other side, okay, remember, was the divergence of, okay, you take Q and minus P. Yeah. In Green's theorem, this is not a generalization yet. So let me forget it. Let me say in Green's theorem. I'm just manipulating the places. I'm writing the same thing. So this happens to be, okay, integral of, now call this your function f dot n, but n is perpendicular to C now. It is double integral of the divergence of f. Now the generalization is obvious. Okay, we have a perpendicular unit normal. We have f dot n. We have a line integral, okay, over C, but it will become a surface. So we have a closed surface. We have f dot n. Of course, this ds will become the sigma. We have a surface integral. And on the right side, we have a triple integral. So that, okay, this closed surface bounds T, okay, and we have the divergence of it. Nothing else. Here, important thing, okay, here S is the boundary, okay, surface of T. Well, this is called divergence theorem. Also called Gauss's theorem. Actually, you have used it in physics in many places. Now, a few final remarks and observations. Okay. For example, in fluid dynamics, well, fluid dynamics means that you have a flowing liquid or gas, basically, or a similar entity, whatever. Okay. In fluid dynamics, del dot v, v is the velocity, okay, must satisfy del rho by del t. Here, okay, rho is mass density. So, okay, if del dot v is 0 at all points in a flowing fluid, what does this mean? Then necessarily rho, okay, is constant with respect to time. So its derivative is 0. Okay. Well, if the density is constant, okay, it means that your fluid is incompressible. That is, its densities don't change at any point. It just moves along. Okay. This is quite obvious for liquids, even though not exactly true. But for gases, okay, this may be very important. Because when you have a gas flow, it's highly probable that at some points they will squeeze, at some points they will just diverge, and so their densities will change in time. Okay, but if it's not true, then, okay, so the fluid is incompressible, i.e., what comes in goes out. Okay. Now, for an electric field, let me say a second remark. Okay. We have del dot E, a multiple of Q. Q is the charge density. Okay, these are all. None of these is constant. K is constant, of course. Let me put here X, Y, Z to show it's not a constant in general. Density changes from one point to another, but we have this equation coming from the Maxwell equations, which govern all electrical, magnetic, and electromagnetic flow. Now, so if for some field we have this zero at all points, okay, this means that by Stokes theorem, okay, this is zero. That's to say, the flux is zero. So, total flux is zero. Now, what does that mean? Well, you have some electric field which should act, but if it acts, okay, on something, it loses energy. So what comes in and what goes out are not equal. In other words, okay, the total effect of this field to any point, for instance, inside the surface S, that's T, is zero. This is because there's no charge in it. Okay. So there is no charge because the right-hand side is zero. Okay. Q inside T. So, okay, this field does no harm. If you are inside. Okay. For example, okay, if you are inside a car, okay, when a lightning strikes, okay, it doesn't harm you. Because all the flux that comes in just goes away to the outside. Okay. But of course, okay, never depend on it. you are not sure that a car, okay, it's a closed surface, that a car satisfies the hypotheses in divergence theorem. Which we did not cite here. Okay. Now there are, I mean, wherever you put your hand in three-dimensional engineering or mathematical structures or physical structures, you always get these types of equations with divergences and curves. Okay. Well, so this would be the end of the examples that I wanted to talk about, but you can find millions of them in the internet if you check for it. But these two theorems will probably govern most of the engineers' lives because they are the basic equations in almost all fields of engineering. Okay, thank you for listening.